Alright, thanks for watching, and today I want to do something really cool. I would like to define the dimension of any set. So not only like one-dimensional or two-dimensional sets, but really fractional dimensions. And we'll see there will be some really cool fractals which have some interesting dimensions. So this should sort of transcend your ordinary thinking about dimension, and I'll try to keep it sort of kind of on the down low, not too complicated. So I won't really go into the details of this, but just intuitively, what is a dimension? So just a little motivation. Suppose you take a ball in 2 dimensions. So just a disk of radius r. Then the area of this disk, it's pi r squared in 2 dimensions. Right? And notice we get the 2 precisely from this exponent. Now, what if you have the ball of radius r in 3 dimensions? Well, bxr, it's simply 4/3 pi r cubed in 3D. So notice the dimension appears precisely in the exponent of the measure of the ball, which will help us to define a dimension. And also, by the way, this is also true for n dimensions. So there's a beautiful video where I calculate the volume of an n-dimensional ball. So it'll be something times r to the n. And in fact, for any number d between 0 and infinity, we can actually define the volume of the d-dimensional ball to be some constant, let's call it alpha d, times r to the d. So in d dimensions. So for example, in 1/2 dimensions, the volume of that ball would be some constant times square root of r. And which also gives us an idea how to define a dimension. So intuitively, and this is kind of an interesting feature of dimension. Suppose you have some region in R2, like a 2-dimensional surface in R2. Well, intuitively what you can do, you can like cover it with finitely many disks. And then you get some answer. So suppose you cover your region with 2-dimensional disks, then you get a finite answer, and in fact, the smaller you take those balls, then you can actually get the exact area of this region using some sort of a limit. And this limit is sort of what's called the Hausdorff dimension. So intuitively, the d-dimensional, so the Hausdorff d-dimensional, the d-dimensional Hausdorff volume or measure of that set S is just the smallest answer you can get by covering this set by balls. So if you want, it's the minimum, or technically speaking, it's the infimum, if you know what this means, of the sum of the areas of the balls where you cover this set with balls. So you can cover S with balls of radii, Ri. Could possibly be an infinite cover, but the idea is if you cover this set with those disks of radius Ri and you add up the areas of all those disks, then you always get an overestimate of this thing, this set S, but the smaller you take your balls, if you kind of take the smallest answer, it would give you the exact answer. Like this one would be a better approximation of your set S. Something like that. You take smaller and smaller balls, and kind of what this means is if you take the limit of those balls, then you get your actual answer. And I forgot to say, where does the D come from? It covers S with d-dimensional balls. and which are just defined by balls with this area. And in particular, well, the Hausdorff measure, like the d-dimensional Hausdorff measure of a ball, of a d-dimensional ball, it's simply like the area of the volume of that ball. Like in 2-dimension, if you have a disk of radius r, then, well, you can literally cover that disk with itself, which is a ball, and there's no better answer you can get with this. All right, so this is a Hausdorff measure. We won't really use that much, but notice we have this nice property. So suppose the Hausdorff measure is kind of weird. It's either 0 or infinity or something in between. So suppose you have now some region, let's say in 2 dimensions. And suppose A is 2-dimensional. Now we know that if we take 2-dimensional balls, in this case we get a finite answer, but what if we try to cover A with 1-dimensional balls? So what are 1-dimensional balls? They're just balls in R, which are just little line segments. And the question is, how many line segments do you need to cover this A? Well, actually you need infinitely many line segments, no matter how you cover A. So it turns out if you cover A with 1-dimensional balls, then the Hausdorff measure will be infinity. In other words, if D is strictly less than 2, you will always need infinitely many balls to cover it. So it turns out this minimum is always infinity. So in other words, if you have D in this case, and this is 2, then the Hausdorff measure here, of A, will be infinity. On the other hand, how many 3-dimensional balls would you need to cover this thing here? Well, actually, kind of just 1. Okay. And this will always be like a huge overestimate. So it turns out because of the minimum business, you can always pick balls, a 3-dimensional ball of very small radius, and basically get that this measure will be smaller than this really small 3-dimensional ball. So it turns out if the dimension, if D is much bigger than the actual dimension, then you get 0. So in this case, HD of A, it's 0. So you see, if D is smaller than the actual dimension, then you get infinity. If D is bigger than the actual dimension, you get 0. And in fact, this is how we can define a dimension of the set, namely the smallest value for which HD is 0. So the Hausdorff dimension, so technically now I do have to use infimum. It's not the minimum, not always attained, but it's the smallest value of D such that the d-dimensional Hausdorff measure is 0. And sometimes for D equals 2 here, you get a finite answer. So like, a positive finite answer, but not always. There's some weird sets for which even with this d-dimensional thing, you get 0. But the point is, what is the true dimension of a set? It's just a transition going from infinity to 0. Just like here, if you cover it with stuff that's less than 2-dimensional, then you get infinity. If you cover it with something that's more than the 2-dimensional, then the measure is 0. Because notice this area, it has volume 0 compared to 3 dimensions. And the only problem is, sure, this is a nice definition, but it's very annoying to figure out the Hausdorff dimension from this. Luckily, there's a very nice property that will help us much easily figure out the Hausdorff dimension. Because notice, it has to do with scaling, and this is what leads me to fractals. That's really cool. Here's a nicer property. So remember the measure of the Hausdorff measure of the d-dimensional ball is, alpha d r to the d. And that's for the d-dimensional ball. If you use d-dimensional Hausdorff measure, now what happens if you scale this ball by 2? And by this, I don't mean take the sum of the two balls. It's just, what if you take the ball centered at x and radius r, and you multiply everything by 2? Or maybe I should be more precise, be 0. Then, if you multiply this by 2, all this means is the radius doubles. And the question is, how does the measure of the bigger ball relate to the measure of the smaller ball? Well, as I said, by definition, this is the measure of b0 to r. And you could actually just plug in this formula. That would be some number times 2r to the d. And that's alpha d, 2 to the d, r to the d. And now let's see what the ratio of this is. So 2b0r. So if you compare the new volume with the old volume, well, this becomes alpha d 2 to the d rd over alpha d rd. So the constants we actually don't care about because they cancel out. The r cancels out, and this is 2d. So in other words, 2 to the d, what does that measure? It measures how the new ball compares to the old ball. And notice this purely just depends on the dimension. So it turns out we can use this property to figure out what the dimension of a set is. In general, then, and again, it might not be true in all cases, but in the next examples this will be true. If you scale a set by 2, then it will be 2 to the d times the original size of A. And again, this will help us figure out the dimension. And in fact, let me give you 3 really cool applications. As I said, it helps us figure out the dimension of fractals. And there are 3 really cool examples. One is what's called the Sierpinski Triangle. Oops. Triangle. And what is this? So if you like Legend of Zelda, you would love it because you start with a triangle. Let's say centered at 0 and 1, and then take out the middle triangle here. What you get is a triforce, in fact. And then, with each sub-triangle, take out the middle triangle. So you have 3 triforces, okay? So it's a triforce. And then continue like that. They always take out the middle triangle. Looks like this. And again, I think on the thumbnail I'll put a nicer picture of this. Or on Wikipedia they have nicer pictures too. And then you just continue, and then what you get is kind of a dusty triangle. So a triangle with lots of holes. And the question is, what is the dimension of this fractal? Turns out it will be bigger than one-dimensional because it includes this segment, but strictly smaller than two-dimensional. And in particular, we want to use this formula that says if you scale the object by 2, it will have a certain dimension. And in fact, notice there's this beautiful thing that happens. Because suppose you take this, you take this set S and you scale it by 2. Then what we get, this segment becomes 0, 1, and 2. And then what you get is a huge triangle here. But look, with this huge triangle, by Sierpinski-ness, you would take out the middle triangle. And then what you're left with really are 3 Sierpinski triangles. Because notice then what you do, you use the Sierpinski iteration on the top one, on the right one, and on the left one. And so this is the beautiful thing about fractals. They're self-similar. If you double it, if you like zoom in, you will find the same picture, but here 3 times. So in other words, what 2s is just like if you scale s by 2, then you get 3 copies of s. In particular, the area, or whatever the measure is of 2s, becomes 3 times the measure of s, because this is 2s, and we get literally 3 copies, 3 disjoint copies of s. Now, why is that useful? Because remember we had this formula. If you scale something by 2, it just becomes 2 to the d times the original measure. So this becomes 2 to the d times s equals 3s. And remember, so the Hausdorff dimension, which like the Hausdorff measure, which shows it sort of that this is not infinity and hopefully not 0. So just for the purpose of this, assume it as a non-zero measure. Then we can cancel this out. And then what's the dimension? So 2d equals 3, which tells us the dimension of this fractal, it's really log base 2 of 3. In other words, if you don't like log base 2, it's ln of 3 over ln of 2. So it's really cool. It's a set that's not one-dimensional. It's strictly bigger than 1, but strictly smaller than 2, because ln of 3 is less than ln of 4, which would make this 2. But this is true, and I believe you can show it's irrational. So it's an irrational dimension here. So it's very, very cool. That's one thing, and it turns out there's this flip thing for another set, which you may have seen in analysis, which is called the Cantor's Middle-Third Set. Middle 1/3 set. Which just says, start with the set interval 0, 1, and take out the middle half at each point. So here, if you take out the middle, which is interval 1/3, 2/3, you get this. If you take out the middle, you get 4 little intervals, and then 8 little intervals, etc., etc. And at the end, you have this dusty set. Now, because we have the middle 1/3 set, we don't want to multiply a by 2. Let's multiply a by 3. And let's see how many copies of the Cantor set we get. So then we get 0, 1, 2, 3. And then you take out the middle third here. Then you take out the middle third here. Etc., etc. And notice in the end, you don't get 3 copies of A. You actually get 2 copies of A. So in other words, the size of 3A equals 2 times the size of A. I guess a Hausdorff measure. And in particular, 3 to the d times A, because of the scaling property, becomes 2A. Assume we can cancel this out, and then we get d equals, so 3 to the d equals 2. So d equals log base 3 of 2, which is ln of 2 over ln of 3. Which is super interesting. In analysis, you learn that the measure, one-dimensional measure of this is 0. But in fact, what this means, of course, it's 0 because it's not a one-dimensional set. But it says this dimension is between 0 and 1. In particular, the dimension is ln of 2 over ln of 3. And lastly, one thing I want to also talk about just for a second. The next one, I don't know quite why it's true, but you do have a similar example with a beautiful dimension. Well, so in other words, suppose you start, again, with the Cantor set, but this time you always take away the second quarter of it. And that's what's called the asymmetric Cantor set. So again, it means you start with the interval 0, 1, okay? And then this becomes, 1/4, 1/2, 3/4, and 1. And then you take off the second quarter. So you have this. And then you start here again. So here you take off the second quarter. And also here. Second quarter. And careful, this is not the Cantor middle quarter set. Middle quarter set means you would take off a quarter of the middle here. But this is slightly shifted. You get this, and then you get smaller sets. And it turns out what happens here, and this is I'm not sure about, you don't quite have a nice scaling like this, where if you multiply your set by a number, you get another set. But you do get that the dimension satisfies the following equation, because it turns out there's some kind of similitude business going on. And it turns out that dimension satisfies the following equation. 1/4 to the d plus 1/2 to the d equals 1. So 1/4 to the d plus 1/2 to the d equals 1. So 4 to the d plus, you multiply by 4 to the d, so 1 plus 4 to the d over 2 to the d equals 4 to the d. And well, this is 4/2, which is 2, so 1 plus 2 to the d equals 4 to the d, and that is really 2 to the d squared. So in other words, 2 to the d satisfies the following equation. 1 plus x equals x squared. So x squared equals 1 plus x. But it turns out what this gives you, so because the dimension, like 2 to the d, is positive, you have that x is actually the golden ratio. It's phi, which is 1 plus square root of 5/2. Because 1 minus square root of 5/2 would give you x negative, which doesn't make sense. So what is the dimension? It satisfies the equation 2 to the d equals phi. So d is log base 2 of phi. So it's ln of phi over ln of 2. So this one, what I like to call it, has a golden dimension. So except for the log base 2, but it's also beautiful. Alright, so I hope you like this fractal adventure. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.